Hello and welcome to section 6.3, where we talk about something called the Gibbs free energy. So before we start talking about Gibbs free energy, let's go back to our talk on entropy. Because in 6.2, we were talking about entropy, but we stayed mostly focused on the energy of the system, right? Because we said that the delta S of the surroundings was a little harder to talk about. So what we're going to do this time is focus a little bit on the delta S of surroundings and how we talk about that mathematically. Because delta S of surroundings does help us to know about the energy of a reaction and if it will be spontaneous. But we still run into the same problems that we did before because delta S surroundings is kind of hard to measure. The really nice thing for us, however, as chemists and scientists, is that at constant temperature and pressure, the delta S of surroundings is actually directly related to the enthalpy present in the system. Because remember, enthalpy is a measure of whether heat is given off or taken in from the surroundings. So we could say that the delta S of surroundings is directly equal to the negative enthalpy over the temperature that we're at. Because as temperature goes up, the enthalpy change goes down, and as temperature goes down, the enthalpy change goes up. Similarly, or not the enthalpy change, sorry, the delta S of surroundings. Similarly, the delta S of surroundings can change, um, they can increase with increasing enthalpy and decrease with decreasing enthalpy. So now, if we plug in to this formula here, our new term for delta S of surroundings, we get delta S, the entropy, the total entropy is equal to this new term, negative delta H over T plus delta S of system, plus the entropy of the system. I've just rearranged where the system and the surroundings are, and which is totally fair in math. Okay, let's try and get that enthalpy term by itself. So we'll multiply each term in this equation by T. There we are. And when we do that, we get T delta S, the temperature times the total entropy of the system is equal to now negative delta H plus the temperature times the entropy of our system. So this chapter is about Gibbs free energy, and you might be wondering when we're going to talk about that. Well, the answer is right now, because this term, the temperature times the total entropy of a system, is simply, or can be simplified to delta G, or the Gibbs free energy. So oh, right, it was by negative T. I'm sorry. I made a mistake there. So it's negative T here, positive delta H, negative T times the entropy of the system. Right, and typically delta G is positive instead of negative. Um, or sorry, typically delta G is the negative temperature times the entropy, the total entropy, but we just simplify it to delta G. And so this leads us to the Gibbs free energy equation, which is that the Gibbs free energy is equal to the enthalpy of the surroundings of a reaction minus T temperature times the change in entropy of our system. And sometimes we talk about it in these terms explicitly, and sometimes we say that we have, let's see, maybe I should write that in sometimes. Sometimes we say, once I change my size, there we are. Sometimes we say delta G is equal to the positive value of the enthalpy plus, or sorry, not positive value, just like the enthalpy as it is, plus a negative temperature times entropy. So saying that, so subtraction is also mathematically the addition of a negative number. So this is totally fair to do in the function as well, in case you were wondering. So by using this equation or this slightly modified equation that I just showed, we can then compare directly the Gibbs free energy to know if something is spontaneous. And just one last little note about spontaneity. Before, up top, we said that in entropy, the total entropy of a system, or there's the total entropy in general, must be positive in order for that reaction to be spontaneous. That is true, but if you look at our delta G equation now, delta G is equal to the negative temperature times the total entropy. So delta G should be negative in order for a reaction to be spontaneous. That is to say, the total Gibbs energy of a reaction, the Gibbs free energy, should go down more negative if a reaction will be spontaneous thermodynamically. And just as we did before with enthalpy, we can actually plot the delta G, the Gibbs free energy, or it should really just be G for Gibbs free energy, with the reaction. And so if our reactants have a certain energy, Gibbs energy, then the change in energy brings us to a lower energy, which means this reaction is spontaneous. And we call this exergonic. I'm not going to draw it, I'm going to write it. Negative delta G is exergonic. Don't get this confused with what you just saw, which is exothermic. Exothermic deals with enthalpy explicitly, and exergonic is what we call spontaneous Gibbs free energy processes. Spontaneous chemical reaction. Conversely, you can have the opposite happen, where energy of the Gibbs energy is increasing for some reaction, and your product energy is now increasing, which means that instead of an exergonic reaction, we now have a positive delta G value and an endogonic reaction. Or is it endergonic? I think it might be endergonic. Yeah, endergonic, sorry. Endergonic, which is no spontaneous reaction. or a non-spontaneous reaction. Okay, so we've learned now how enthalpy and entropy directly relate to the Gibbs free energy, and we'll be talking a lot about Gibbs free energy in this chapter. So prepare yourselves, and I hope that this has been useful. This has been section 6.3.